Welcome friends, in this video I'm going to give you a kind of, Bob the Builder introduction to vectors. This is what I mean. Take a look. Here's my finger. And I want to be able to represent mathematically something like, for example, a displacement, a vertical displacement. Take a look. This is the table. I'm displacing vertically and I stop right there. That's a vertical displacement above the table, the way you see. I want to be able to, for example, represent that using some kind of mathematical formalism. I'm not going to write any math. I'm just going to show you instead. I think it's more convincing, to be honest. Let that be a vertical displacement of 1 unit. We call that the k vector. It goes 1 up. It could be 1 meter, 1 centimeter, 1 inch. It could be one of whatever the units are that you are using, but it has to be 1. So that then normally is written as 1k. Then the next question, naturally enough, is how do you represent, for example, like a displacement of several units in the vertical direction? I'm sure you can guess already that you can simply take this and just stack it out vertically like this. Take a look. So that would be like, for example, a displacement of 2 units in the vertical direction. This here would be like a displacement of 3 units in the vertical direction. You see? You're stacking them vertically. That there would be like a displacement of 4 units in the vertical direction, and so on. So that's one possibility. So that would be like, for example, if I wrote this on paper, this would be 4k. Okay, a displacement of 4 units in the vertical direction. That's one possibility. So that's if I'm going vertically straight up. What else can I do? Well, I can also, naturally enough, I can also build up, look, I can also build up the same thing by going in like a direction perpendicular to the first one. That there often then might be called something like the I vector. That means 1 unit along, for example, this direction right here. Often called the x direction or the x-axis. I'll get to the coordinate system you see behind there in a second. So that would be like 1i, and then therefore this here, take a look, would be like, for example, 2i. And then this right here, that would be like 3i, for example. There's one last direction, take a look, which is this one in this direction. Take a look. I'm going to take it this way. You see that there, that blue arrow now, like this one right here. Let me make sure you can see it. You see, that could represent 1 unit along the y-axis. So that would be put like in this position right here, see? And then to represent, for example, I would call that a j. That would be called 1j. It's a unit vector along the y-axis. And then naturally enough, what you could do after that is stack out several of them. I'm going to shorten the vertical one so it doesn't tip over so easily. And I'm going to stack out some of these blue ones that represent unit vectors along the y-axis. You see it looks like that. Now I'm going to rotate the camera a little bit so you can see it from different angles. That's important when you're dealing with 3 dimensions. See that? The purple ones are basically 3z, the yellow ones are 3i, and the blue ones are 3j along the axes of space. Remember, space is 3-dimensional. So what use is this? Well, the use is that now other vectors in 3 dimensions can be represented as a combination of vectors along the 3 dimensions of space. Take a look. I'm going to reposition it this way for a second. And what I'm going to do is just grab some other vector, like for example, this vector right here. Orange vector as given in this position. Okay, look, this is a vector. See that? Now, when you are in 3-dimensional space, obviously, the number of ways you can point, see, that is virtually unlimited, right? You can point in so many different directions. A little bit this way, a little bit that way, a little bit this way, a little bit down, a little bit this way, and so on. So, we're going to formalize this a little bit. I've built up my little, unit vector coordinate system essentially. And now, imagine I want to be able to represent this vector using those unit vectors along the 3 coordinate axes of space. How can I do that? Well, take a look. Imagine that this is my vector, the way it's hovering right here. And I'm going to reposition my coordinate system so we can visualize things better. It has to be done from a right angle so we can see it properly. Look, you see how it's kind of pointing this way? So what I can do as an example is imagine the following, that I'm going to move these aside for a second, that I'm beginning over here, right here, and what I'm going to do is just travel along that vector, and I'm going to stop right here. That's just a motion. Maybe I'm climbing like a flight of stairs or something. That's equivalent to doing this. Take a look. It's as if I went, for example, this way. 2 units along the x-axis, Then if I went, for example, like 3 units along, as you can see there, the y-axis, and then on top of it, it's as if I went, for example, 2 units along the z-axis, like that. And you see that motion is equivalent to just going along the orange one in the first place, like that. So you say, why not just go along the orange one? Why are you introducing all of this stuff around it? And the reason is simple, because we live in 3-dimensional space. So that yellow one would lie along the along the x-axis. The blue ones would be along the y-axis, and those would be along the z-axis, because that is how 3-dimensional space kind of is constructed. You can see that when you look in the corner of a room, right? You see 3 things meeting, 3 different planes meet in the corner of a room when you look, for example, where the ceiling and the 2 walls meet. So if I had a displacement along the orange one, it would be equivalent to going 2 this way, 3 this way, and then 2 straight up. Let me make sure that you see that vertical dimension this way, right here. You see that? Make sure you see it. Okay, that it really is 2 units above the table. Okay, I hope you've got that. Now, that's one possibility. What if I want to represent like something like a push? Now remember, when you push in 3-dimensional space, think about this for a second, right? Imagine this is like 2 objects, 3 objects. My fingers, they're pushing, say, against each other like this. Look. Okay, I'm pushing right here. I need to be able to represent this in some mathematical way. Like this finger is pushing this way. This finger is pushing this way. See that? They're pushing against each other. And now this thumb is pushing this way. So now I have 3 pushes. Those are 3 separate forces going basically in like almost opposite directions. They're perpendicular to basically one another. Okay, this is hard to obviously simulate with just fingers, but I think you get the idea. So how can we represent pushes? Imagine that this is what's going to happen. Take a look. If I push the right way in all of these perpendicular directions, the result will be for my hands to travel along this line right here. You see this? If I push the right way. In other words, a vector like this one in 3-dimensional space could represent a push. The result of combining, say, 3 other pushes into one push. The resulting behavior of something. Look. So that could be simulated by doing it this way. Take a look. Those 2 yellow vectors could represent the push of this finger, like in this direction. You see this? Oh boy, okay. See, it's hard to hold sometimes. So this here could represent the push of 2 in that direction. You see? That's why I need these 2. This one right here, okay? That could represent like the push, say, of the thumb in that direction. You see? That's why you need that. Lastly, depending how I arrange things, obviously, I can also be pushing up. So these 2 might be needed because they represent, say, a push of 2 units in the vertical dimension. Then the cumulative result of those individual pushes would be represented with this vector right here that you see. Because, for example, an object would end up moving along that direction. So that push would be built up from pushes along the individual axes, the way you see here. Keep in mind that arrows, like vectors, are basically mental models. They don't actually exist, except in our minds, because when you're actually pushing on objects, right, like my fingers here are pushing against one another, I don't see any magical arrows pop out, right, to show me how I'm pushing. The only thing I experience is the feeling of pushing. And that feeling of pushing, the strength of it is represented with a vector, okay? The same thing also with direction, right? If I'm pushing straight down, my vector would be this quantity right here, pointing straight down into the table. If I were pushing straight up, like this with my thumb, for example, like up this way, that would be represented by having a vector pointing straight up, you see? Lastly, I'm going to take all of this, I'm going to bring it into 3-dimensional space. So this is an example of 3-dimensional space. That's the y-axis. That there is the z-axis, and that there is the x-axis. And you can lay your vectors here. Take a look. For example, that there would be like 2k, as an example. That there would be like, say, 2i, like that. And lastly, for example, this one, for whatever reason, might be like, for example, 1, 2, 3, 4, j. Let me zoom in on that. See that? And then any other vector floating out here in three-dimensional space could be represented as a linear combination of those unit vectors, as I have already demonstrated with this simple push example and a displacement example. Thanks so much for watching. If this has been helpful, please leave a like, and I'll see you in another physical math video.